3, 2, 1. Dr. Payam.
Alright, thanks for watching. And I got a request to calculate the integral of 1 over 1 plus x to the 6th. Well, you know what? I take you 6 and raise it to the power of n over 6. So here I will actually calculate the integral from 0 to infinity of 1 over 1 plus x to the n, where just one thing, n is greater or equal to 2. And n is an integer, and how am I going to do this? Of course with complex analysis, you know. What else? Haha. Okay, so just a little, I guess a prelude, maybe step 0 or something, step 1. Let's first of all figure out when the denominator of this is 0. And you'll see, usually it's a bad thing when the denominator is 0, but here is actually pretty crucial. Okay, so let's see. 1 plus x to the n equals to 0. Of course, this implies x to the n is minus 1, but we want to be a bit more clever than that. Let's write minus 1 in the following form. Again, using complex analysis. So x to the n is ei pi, okay, times 1, which is, of course, ei 2 pi m. Because my name is not 1, my name is pi m. Okay, so with m equals from 0 all the way up to n minus 1. Because after that, you know, we just have a repetition. So then we get x equals to ei pi over n, ei 2 pi m over n. Okay, again, m goes from 0 to n minus 1. Again, after that, there will be a repetition. So if you want in the complex plane, we can just write this as ei pi over n. Again, n is fixed. Ei 2 pi over n, etc., etc. You know, ei 3 pi over n, blah, 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 up to ei, again, 2n minus 1. So I guess, 2n minus 1 over n pi. Or if you want, this is the same thing as ei minus pi over n. And the question is, how will we evaluate that integral? And it's very interesting. Basically, just as in a previous video, we want to integrate over a sector, and that sector will precisely be a sector which consists of a straight line, a circle, and another straight line that goes precisely between those two things. And now I realize I made a small mistake. That should be ei 3 pi over n, ei 5 pi over n, all the odd things. Okay? So we want to go through a sector with a line that goes to precisely those 2 points. Okay? And of course, let's do that. And the nice thing is, we will just ignore all the other singularities. So, here's the second step. So step 2, our contour. Okay, so we have the following. On the one hand, a sector that starts from 0 to r. So let's call this A. We have, of course, a singularity, ei pi over n. Okay, and then we also have, again, the other singularity, which is ei 3 pi over n. And you may ask, what about ei 2 pi over n? Well, we want a sector that goes precisely through that point, namely the point r ei 2 pi over n. So at some point we will visit that point as well, ei 2 pi over n, which again, strictly speaking, is not a singularity. This point is just ei even pi over n, which is not a singularity. And so this becomes a contour, let's call it C, which consists of 3 parts, A, B, and C. And of course, one of the theorems is that we can decompose a complex integral in terms of the 3 parts. So the function we want to integrate is 1 over 1 plus x to the n, but with z, 1 plus z to the n dz. And the point is, this consists of three parts. The integral of a of 1 plus 1 plus z to the n dz, plus the integral over b of that part, plus the integral over c of that part. And you'll see, it's not too bad. Definitely much better than some other integral I've evaluated. So let's first study A. So step 3, study of A. Well, this contour is not too bad. You just want the straight contour going from 0 to r. So gamma of t would be t, where t goes from 0 to r. And the nice thing is the derivative of that is 1. So the integral of a of 1 over 1 plus z to the n dz is just the integral from 0 to r of 1 over 1 plus t to the n dt. Again, technically, phi prime of t times dt, but phi prime is 1. Oh, gamma prime is 1. Sorry. And then the nice thing is, if you let r goes to infinity, okay, this becomes precisely what we want, namely 1 over 1 plus t to the 4th dt, where t is real. And let's just call that I, because you'll see later we want to solve an equation involving I, which is good. So we found our first path, and now let's study B. And notice B is precisely, a sector of a circle. Thank you. Okay, amazing cameraman. Okay, okay. So the second part is just a sector, namely a chunk of the circle of radius r. Okay, thank you. Okay, so study of B. B, and that's step 4. And the point is, on B, we actually have that the modulus of z equals to r, because we're on that part of the circle. And notice there's a little fact that we need, because we want to show that z to the n plus 1 is greater or equal to something. And the problem is, usually you might think triangle inequality, but triangle inequality goes the wrong way. So here we want to use an anti-triangle inequality, which is called the reverse triangle inequality, which just says that a minus b, the distance of a minus b, is always greater than or equal to the distance between their absolute values. And this, interestingly, you prove using the triangle inequality. So in particular, this becomes z to the n plus 1 is greater or equal to z to the n minus 1. Okay, and here you just use the fact, again, that z to the n plus 1 is z to the n minus 1. So our a is z to the n, and our b is minus 1. So in the end, this becomes absolute value of modulus of z to the n minus 1. But remember that modulus of z is just r. So we get absolute value of r minus 1, which, if r becomes large enough, is r to the n minus 1. And again, you might say, hey, this is all wrong, but not quite, because now we want to take 1 over our integral. So, integral over b of 1 over z to the n plus 1 dz. Then, by the regular triangle inequality, it becomes 1 over absolute value of z to the n plus 1 dz. But now, using an amazing inequality, we get the integral of b to the n of 1 over r to the n minus 1 dz. But notice, this does not depend on z, so we get 1 over r to the n minus 1 integral b of dz. But the integral of 1 is just the length of the curve, so we have this equals to 1 over r to the n minus 1, the length of b. Okay. But then b, let's see, the length of b just becomes, if you want, let's see, so it's 2 pi r times the length, or I guess maybe pi r of, let's see, pi r times the angle, or not even that, let's just say a constant times pi r, just to make our life easier. And then the point is, because n is greater than equal to 1, because n is greater than equal to 2, this actually becomes r over r to the n. And if n is greater than equal to 2, the point is, as r goes to infinity, this goes to 0. So, in fact, the second part goes to 0. And again, no concavity, nothing crazy, okay? And by the way, you may say, what about n equals to 1? It turns out if you do the integral, it automatically diverges. So let's forget about 1. So that's good. It's much better. And now let's study our last contour.
That looks like a donut, by the way.
Huh? Donut.
Like a donut.
Oh, it does, huh? It's very delicious. So it's a delicious value. In fact, it's the value you get after I eat a donut. After a donut, you get 0 donuts. Lastly, we want to, well, almost lastly, antepen something lastly, we want to evaluate the integral along this last path, C, and notice precisely, it has to go through the point ei 2 pi over n. So maybe step 5. Step 5, study of C. So here, let's use a point, a parametrization that starts at this point and that goes to 0. And precisely it's gamma of t equals to ei 2 pi over n r minus t. And that in fact works because it starts at ei 2 pi over n and it ends at 0. So t is between 0 and r. And then if you calculate the derivative, gamma prime of t is minus ei 2 pi over n, okay, just minus ei 2 pi over n. This ei business makes me think of old MacDonald, Old MacDonald had a farm, ei 2 pi over n. Anyway, okay, and so this last integral becomes 1 over z to the n plus 1 dz equals to, so integral, again, from 0 to r of 1 over this horrible thing, ei 2 pi over n, r minus t to the n plus 1. So this is just z to the n, okay? And then the derivative, so minus ei 2 pi over n dt, okay, and you'll see this horrible thing is actually not too horrible. So let's first of all factor out the ei 2 pi I over n, integral from 0 to r of 1 over, so ei 2 pi over n to the nth power, so in other words, times n, okay, and r minus t to the n plus 1 dt. But look, this n cancels out, and then ei 2 pi, that's just 1. So this horrible thing equals to 1, and you're left with the following, minus e 2 pi I over n, integral from 0 to r of 1 over r minus t to the n plus 1 dt. And now I know some people are very excited, and yes, I can leave it, relieve you suffering. Let's do a change of variables. So let's u is r minus t, and then du is minus dt. So we get, maybe let me do it on another blackboard, do the change of variables. We get minus e 2 pi I over n, and then 0 becomes r becomes 0, 1 over u to the n plus 1, and minus du. Now, notice the orientation here is completely messed up, but because of this minus, we rebuilt that orientation, and we're left with minus e of 2 pi I over n, integral from 0 to r of 1 over u to the n plus 1 du. And now we're ready to let r go to infinity, and we get minus e of 2 pi I over n, integral from 0 to infinity of 1 over u to the n plus 1 du. But lo and behold, this is precisely our integral from the beginning, so we get minus e of 2 pi I over n, I. Fantastic! So we have our three pieces, and let's put them together by actually evaluating, the whole integral. So step 6. Now, we have the three pieces, and now let's consider the integral over the whole contour. So 1 over 1 plus z to the n dz. Again, here is where the complex analysis comes in. It turns out this equals to 2 pi I times the residue at z equals to a singularity, so ei pi over n, of 1 over 1 plus z to the n. And this is nice that we just chose one singularity, otherwise we would have a sum of those. And here's a little fact, and maybe I should do a video on residues one day, but the residue at z equals to some point, z naught, of a fraction, g of z over h of z, that's just g of, so the numerator, you just evaluate it at 0, at the point, and the denominator, you differentiate it, and you evaluate it at the point. Which becomes very nice here, because look, the numerator is just 1, so you still have 2 pi I times 1, and then the derivative of that is n z to the n minus 1. So all you do is you plug in ei pi over n over that, ei pi over n. And now let's see how to simplify this. So you get, again, 2 pi I, maybe let's put this here, equals to 2 pi I over n ei pi over n, which becomes ei pi, and then e minus I pi over n. But the nice thing is, ei pi, that's just minus 1. So in the end, we get minus 2 pi I over n, and then 1 over e to the minus I pi over n becomes ei pi over n. Great! So in other words, the whole integral is just minus 2 pi I over n, ei pi over n. And now let's put everything together like an exciting witch or something. Now step 7, here's our grand finale. Because on the one hand, we have the result from the whole curve C, so minus 2 pi I e of I pi over n, that's from C, equals to, so A, which gave you I, plus B, which gave you 0, plus C, which give you minus EI, 2 pi over n, I. Which means that, in fact, we can solve for I. So in other words, this becomes I times 1 minus EI, 2 pi over n. And then, so one thing you can do is just divide both sides by EI pi over n. Again, also EI pi over n. Again, because we want to write this in a nice form. So we get minus 2 pi I over n equals to I times E of minus I pi over n, okay, minus EI 2 pi over n minus pi over n, which is pi over n. Okay? And we're almost done. So then let's just divide both sides by minus 2i. So divide it by minus 2i. And we divide it by minus 2i. Okay. Then we're left with so pi over n, so it's almost me, equals to EI pi over n minus E minus I pi over n over 2i. And again, the two things are reversed because we divided by minus 2i. But in case you know complex analysis, you might recognize this as sine of, sorry, I forgot the capital I. You recognize this as sine of pi over n. Over n. So what do you get? Pi over n is I times sine of pi over n. So I equals to pi over n over sine of pi over n.
Wow.
Cool, huh? So with one complex analysis trick, I evaluated them all.
Oh,
it's like
wow.
this Pokeball that catches all the Pokemon at once.
Sing a song.
Huh?
Sing the song.
Oh, Pokemon! Da 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 da.
Listen to the song. Gotta catch it all, Pokemon.
I just know the German version.
Wow.
Go ahead.
Huh? Wait, I forgot the German.
It's okay.
There's one little remark. You might say, what about the integral from minus infinity to infinity? If n is even, it just becomes 2 times that. But you may say, what about if n is odd? It turns out I believe that the integral is divergent because you have a singularity on the real axis. Like 1 over x cubed plus 1, it has a singularity at minus 1. And I believe because of that, the integral is divergent.
Oh.
Alright, I hope this wasn't too complex for you, but if you like that and other math topic, please make sure to subscribe to my channel.
Yay!
Yay!
Woo!
Woo!
Complex.
Woo!